activity. G'day, my name is Brendan, and I'd like you to imagine that you have a server that's running at 90% CPU utilization. What would you do as a performance engineer given this server that looks like it's CPU bound? What are the next steps for analysis? Does someone want to try? Imagine this is a job interview question at Netflix for the job, the senior performance engineer job that we just posted. Yes? Look at the queue length. Where's it spending its time? What tool would I use for that? What tool would I use for spending its time? Which one? Sorry, the VMstat. VMstat's very high level. Use the system breakdowns. I can look at the queue length to see how badly we're saturated. Flame graphs are pretty good. I mean, flame graphs are pretty good. So flame graphs will show you whereabouts in your code that you're spending time and what might be some of the rectifying. So now we've talked about some of the tools to analyze this. What would be some of the rectifying actions to make this server perform better? Kill -9, kill the application, eliminate unnecessary work. Now think about it. You've run a flame graph, you've got some time in a particular piece of code, or you've got saturation on the CPUs because the queue lengths are high. What are some of the rectifying actions we take for CPU utilization? Refactor the code. I mean, change the code, take out the unnecessary work. What about hardware changes? Add more capacity, that's going to work as well. Bigger instances, faster CPUs. So that's basics, and I do go through this in job interviews. However, and I don't like to do trick questions in job interviews, in reality, this does get pretty tricky. So this is modeled on what our production servers typically look like, and that is where we spend about 20% of time is making forward progress on instructions, and about 70% of the time is waiting, stalled at the CPU level. So for some definitions, busy is, in this case, is when the CPU itself is making forward progress, whereas 90% busy is for the first graph I drew, is an operating system metric. So that's what you typically measure. That's what a lot of your tools will show. But at the CPU level, it can either be making forward progress on instructions, or the CPU itself can be stalled because it's waiting for an external resource. That's often waiting on memory I/O, waiting on a bus, or something else. We might be doing thermal trips, and it's doing thermal cycles. Given this, there's a whole different type of rectifying actions that we need to take to make performance better, to attack the 70% of time we've got installed. Instead of focusing on the 20% of time, eliminating unnecessary work or buying faster CPUs or scaling up. If we buy faster CPUs, what ends up happening is we stall faster. And so you make the busy component a little bit better, but then you're just able to stall more quickly on main memory. So this is a big problem, and it's also a big opportunity for us to be able to understand this. And it's so fundamental to what we do as well. So Vadim talked about scaling up and how much effort and work we've gone into to make sure that our scaling policies track the target closely. The target that we often set is based on CPU utilization. And so this is a very important metric for us to understand properly. Fortunately, there are tools. Has anyone done PMC analysis before? Great, so we've got at least a dozen people. On Linux, there's perfstat. And if you run it in the cloud, unfortunately, you get this, not supported. So last time I talked about PMCs, I gave a talk with Jim Marrow when we were working at Sun Microsystems. Since then, I've not done much PMCs because of the cloud. And the cloud, I've been working on the cloud. The cloud blocks PMC access from guests. PMCs are performance monitoring counters. They're this low-level counter that the CPU you can access on the CPU by doing some MSR instructions and doing RDPMC, but they will cause a trap into the hypervisor can then gate it and decide whether the guest can do it or not. And the way these are set up on all clouds is the hypervisor will disallow PMCs. I really wanted PMCs. So I started looking at the Zen source code to see how possible it was. And fortunately, Zen already supports PMCs. In fact, many hypervisors already support PMCs. But they're not turned on in the cloud. And the reason it's hard to know, it may be security. I mean, it depends on the cloud provider. And if you go to a cloud provider and you say, why aren't you turning this on? May it be security vulnerabilities? Suddenly cloud providers can be very protective about it because they're sensitive and they want to look after their other customers. They don't want to say, yes, there's this huge vulnerability. It's no, we just won't turn it on. It's for security, end of discussion. So I really wanted to turn this on, and on the assumption that it may be security related, I did some research into PMCs and security and found that there have been vulnerabilities. Except these vulnerabilities are very unlikely to happen. You need to be able to run perfstat directly on a binary, and then, I mean, if you can run the binary itself, you can just run it through a debugger. If you run it directly on a binary and then you're pulling out cache information, there's various attacks you can do. Very, very unlikely. But if you think about it, if security is the concern, then instead of enabling all the PMCs, and there are thousands of PMCs, let's just enable enough to get our jobs done as performance engineers. And I modified Zen to expose just enough PMCs and had that change upstreamed. And Amazon have recently, this year, deployed it. And now you can run perfstat on dedicated instances, and it looks like this. So we get to see cycles, instructions, branches, branch misses, and some other counters, which is great. It's fantastic. And so for the first time, I get to see instructions per cycle, which is a key metric for understanding what the CPUs are doing. Now, of course, Amazon are very protective about how they did this, and I don't know if they used my code or they completely rewrote it, but I'm just happy that it's now there. So now I get to talk about PMCs again, because they are very useful, and as we know, we're spending a lot of our time stalled on main memory. Instructions per cycle, how to interpret this. Now, I've highlighted it because it's probably the #1 metric, just like a load average or a percent CPU is the #1 metric for understanding a server. The #1 metric for understanding low-level performance is IPC. IPC is how many instructions are retired or completed for each CPU cycle. Now, 0.82 sounds like a pretty good number. Sounds like light speed would be 1.0. But as it turns out, processors for a long time have employed a superscalar architecture where within the processor, it has multiple functional units that can do instruction, fetch, ALU in parallel. And when an instruction comes in, it will be broken up into micro-ops. Those micro-ops can be executed out of order. And at the end of all of this, with every CPU cycle, the processor can retire multiple instructions. Modern CPUs at the moment can do 4 instructions with each cycle. That's maximum, that's light speed. And so they call them 4-wide CPUs. So the maximum speed of the CPU is actually 4.0 for instructions per cycle. And this is doing 0.82. So there's a lot of room for improvement. You won't get to 4.0. You will if you run a NOP loop, if you run the no-op instruction in a tight loop. For a production workload, I would expect it to get to at least 1.0, and with some tuning to get to 1.5. Now for Netflix, that's huge because that will give us a very significant win for many of our instances to be able to go there. Another way to describe instructions per cycle is it is like miles per gallon for the car. The resource that we're spending, the resource you're spending on a car is gallons, and you're getting out of it miles. And here the resource you're spending is cycles, and you're getting out of it instructions. And so you always want the best miles per gallon for your car, and you want the best IPC for your CPUs. How to interpret IPC. Now again, this is based on a 4-wide CPU. So at some point, CPUs are going to go to 5-wide and then 6-wide. And so you're going to have to adjust this point as that changes. In fact, since things do change, one thing I recommend to people is if you can write an application that you know is CPU bound and write an application that you know is memory bound, then measure IPC for your known applications. And so you can figure out your own ballpark figure of what's good and what's bad, or what's memory bound, what's CPU bound for your runtime in your language. So IPC less than 1.0 for a 4-wide, you're likely memory stalled, like we are for many of our instances in the Netflix cloud. Given that you know that, you can fix it by changing the data usage and layout to improve CPU caching and memory locality. There's this whole science, especially in Java performance tuning, of doing data locality, including things like using an array instead of using a hash map. But it's a lot of engineering work if you want to go and change your code, and it really helps to be able to measure it first so you know that that's going to pay off. Otherwise, you're shooting in the dark. You can also choose larger CPU caches by making a hardware decision. You can have faster memory buses and interconnects as well to improve that performance. If your IPC is more than 1.0, so you're at 1.5 or 2.0, you're likely instruction bound. And so now it's about eliminating the instructions, finding out what they are, doing a flame graph, doing a profile, and finding areas to eliminate unnecessary work. Hardware changes you can make include scaling up the CPU, finding faster CPUs, and also scaling up the microservice as we use at Netflix. So this is just an introduction. This is like the first stopping point when you get into PMCs, IPC. What's the IPC for my instance? And then when you figure that out, there's a lot more PMCs to drill down further. The architectural PMCs that we enabled in Amazon EC2, now these are only for full dedicated instances, so you need like a M4.16XL. These are special because Intel have put these in the CPU ID instruction, in the CPU ID binary interface. So when you call CPU ID, you can find out various information about the processor, including which of the architectural PMCs are enabled, which is pretty crazy because there's a lot of PMCs. There's hundreds and hundreds of PMCs. But they've picked these as the top crucial 7 to measure. You have unhalted core cycles, instructions retired, unhalted reference cycles. These can be helpful so you can determine how much you're turbo boosting. Using the instructions versus cycles gives you IPC. We have last level cache references and misses. A last level cache is the largest cache, hardware cache. And then you've got branch, instruction, retired, and branch misses. This is pretty good because it gives you a lot more information about where to tune on the CPU. Tools need to make use of this. So I've got a very quick tool that I wrote called PMC Arch, which just does all I can with those 7 architectural PMCs in counting mode. And that's where I'm counting them per second. They can be used in different ways. You can use them in sampling mode and get stack back traces and program counters out as well. So I put this on GitHub. It's a very simple shell script, but I'm printing out columns for each of the 7 counters and doing things like here's the IPC, here is the branch prediction miss rate, and here is the last level cache hit ratio. So really useful. There's not that many other tools that use PMCs yet. An example of one that has done a lot with PMCs is Intel vTune. But of course, you couldn't run Intel vTune on the cloud until now. At least now you get 7 PMCs. But one I wanted to mention is TipTop. TipTop is a version of Top that gives you a column for IPC and some other PMCs, which is pretty good. So it's showing you the instructions per cycle for each process. At Netflix, I'm already using these to analyze what's going on and get the feel for the cloud and where our bottlenecks are, and we're going to look at monitoring them 24/7. Facebook already monitors the architectural PMCs 24/7. Google, I know at least use IPC, or sometimes it's referred to as the invert CPI, cycles per instruction. Google had an interesting paper, CPI squared, where they're using CPI to find out which instances when you put a new workload on an instance that interferes with the caches, maybe you should move it somewhere else. It's a fairly interesting use of this higher level metric. It's going to get more important in the future. So back in time, processor vendors were scaling CPUs by making them faster, and there was the CPU DRAM gap. And that's where CPUs were outstripping the speed of main memory. That stopped in around the year 2005 with 3 gigahertz processors. Nowadays, processor vendors are scaling up by adding more cores and more hyperthreads, and also multi-socket configurations. These all put more pressure on the memory buses, and the speed of the memory buses and the size of the caches are not increasing at the rate that the CPUs are scaling. And so we still have this gap, and this is why this type of analysis is so important. Thank you.
Thank you, Brendan. So we're going to start setting up for